So these were two scientists, Michelson and Morley, that did an experiment. They were testing for one thing, but what did we get out of it? What did it show the world? They were disappointed, but now they're famous. So your lesson is, and if not yours, when you have a kid that has to do a science fair project and they're all disappointed that it didn't work, you can refer back to this. We learn more often from things that don't go right. Actually, if you always predict correctly what you think is going to happen, and then you do it, and that's what happens, you're not learning anything. You already knew it. So whether you remember this experiment or not, you might realize just from the answers which one's right. This was that interferometer where light went one way, and the light went a perpendicular way to that. They came back together and they detected if there was any difference in the path length. By the way, I don't have to get into the grimy details, but somebody way early on in the class that sat over here had heard about it, and now they've announced it from LIGO, Laser Interferometer, a gravitational observatory. If you've seen anything in the news or whatever, they've discovered gravitational waves, direct evidence of it. It was predicted by Einstein 100 years ago, and they've seen indirect evidence, but this is where they actually directly detected gravitational waves. It's a wave in the space-time itself. And they did that using a huge interferometer. You've probably seen pictures and you see like a line going this way and a line going this way. It's like 4 kilometers one way and 4 kilometers another. But basically they were doing that. They were trying to detect any difference from those two paths when they came back together. The essence of that experiment was an interferometer. Anyway, in this case, it worked and they detected what they wanted to see, announced it, and we're going to learn lots of more things because of it now. All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, still just 39 of you. All right. Oh, you guys are split between A and B. So either the speed of light is not relative or the speed of light is relative. All right. Now you know it's between A and B. You want to talk to your neighbor and re-vote? That was split mostly 50-50. It's one or the other. Find someone that thinks opposite of you and see what they're thinking. What are the consequences of if it's not relative versus if it is relative? Ask yourself, if you don't think it's relative, what is relative, or vice versa? Maybe that'll help you clarify. I know some of you aren't sitting next to people, but it'll help you if you talk it through. Especially if you're feeling like you're not certain of your answer. You know you're right, huh?
No.
Oh.
They said no man's not.
Yeah, I think you're the farthest away from me. Well, here, what were you thinking?
Well, I put down answer A because the speed of light never really changes, only motion, at least from what we saw yesterday. It took light longer to get there, but it still traveled at the same constant rate.
So because speed of light's a constant, so it can't be relative to anything else? That's that going what you're going with?
Yeah, pretty much. Motion itself is relative to spaceship, and at least.
Motion's relative. Okay. All right. That's logical. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. I know there's at least 2 more of you out there. Come on, 39, where are you at? Oh, and we gained somebody. Oh, more of you have shifted to A. It worked. Yeah, the speed of light is a constant. Period. End of story. Finito. What's it in Greek? Do you know? No. If it's constant, then it's not relative to anything. It's the one thing that's true between every different reference frame. What is relative? Space, time, our motions, but the speed of light. how fast light goes, we all get the same measurement. Yes?
Well, wasn't there an experiment about trying to find a
Absolute reference frame. Yeah. So maybe what you're thinking, the point of the Michelson-Morley experiment, have you heard of the ether?
Yeah.
They thought light maybe needed a medium to travel through it, as the book talks about more than I did last time. Sound needs a medium to travel through. We make the air vibrate, and that's how it gets to your ear. But light doesn't need anything to travel through. But they thought it did, because everything else did. They call it this ether. You wanted to say something?
No, yeah, I just get some. There was like a direct correlation. And figure out if there's an ether or not, and the speed of light not being relative. Like, is that, I guess that's the conclusion you made.
It's more, maybe I just reword that to say what they found out that was no frame of reference was absolute or preferred. Thus, the speed of light was not relative to any main reference frame, the ether. They were trying to detect it, never saw it. They got a null result, which has now proved to us and shown that just this. Light can be split into parts. It's true, but that wasn't what the experiment showed. They already knew how to do that. That's called a distractor. Other questions or concerns, comments? It was a great, clever experiment in the day. All right. This has to do with the other postulate that the special theory of relativity is based upon. Oh yeah, good job, Thomas. You were right last time. Your explanations were right on. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Mostly D. Correct. It's actually postulate 1, but who cares the order? Einstein stated that all the laws of physics are the same. And if you're leaning towards C in all reference frames, the only difference between C and D is they just specify which reference frames. Inertial, where you're at uniform motion, constant velocity. In other words, we can trust the law of inertia and everything we've been learning. Or non-inertial, where they accelerate and things are changing. We saw in a little video last time that that's when things get funny and you start having to make up fictitious forces that aren't really there. So his postulate is it's only in uniform moving frames of reference, where the frame of reference is not accelerating. We call these inertial reference frames. And we expect all the laws of physics to hold true in all of those reference frames. Given those two things, well, we can have fun. Let's see, let's do... How about this one? With simultaneity. Things that occur simultaneously in one reference frame. What if we look at a different reference frame? This is one of the results of those two postulates. If you forgot our little video or animation with the train and the lightning bolt strikes, that has to do with this. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Bang. Most of you be correct. May or may not. Those of you that did C, I might go give you credit anyway, because most of the time it seems like they're not simultaneous. But there could be certain circumstances and situations where they both agree, depending on their relative motion to each other. So they may happen to work out to where they agree, but most of the time they don't have to. The definite point here is it's definitely not required. They could seem not simultaneous to one at the same time they do for someone else. And who's correct? Both. They're both right in their frames of reference. That's where most of these arguments come in. And I have a friend that's been trying to grapple with this for years, and I think it disturbs him. He just can't accept that both could be correct. But that's a funky result of relativity. One more. This one might seem a little harder, but I'm going to ask it anyway. C is the speed of light. So if the spaceship's going the speed of light relative to us here on Earth, and then it shoots a drone out forward in the direction it's moving at the speed of light, what do we see the speed as? Yeah, so here we are, and we see this ship going, and while it's going, it shoots out a drone at the speed of light relative to it. Or if it helps, let's say you're on the spaceship. You shoot something out. You see it going at the speed of light. What do we see here on Earth? I guess we got most of you. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. I know there's one more of you. There you go. Split between C and D, but most of you are going with A. The A's have it. Our first question, you could fall back on that. The speed of light is not relative to anything. It's a constant. That's your tip-off. If it's constant, it's not changing. Everybody measures the speed of light. What's throwing us off is we're used to Newtonian physics here on Earth going at speeds remarkably slower than the speed of light. And what is true is if you're on a train going 50 miles an hour and you throw a ball from the train at 10 miles an hour. So you're cruising and you throw this out. What's the speed of the rag relative to you? Train's going 50. From my perspective, I threw it at 10. What do you see? 60. They add. And if I threw it the other way at 10, speed relative to you, I'm going 50. If I throw it at 10, I'm obviously not. You see 40. What do I see in both cases? 10. That's what we're used to. Because of these postulates, the speed of light being a constant, not relative to anything, everybody's going to measure the speed of light. So if I'm going the speed of light, or 80% the speed of light, and I turn on a flashlight, what do I measure the speed of that light beam? C. What do you measure it as? Looking at me, not moving. C. They don't add. That's another kind of oddity. And people have tested this, and it agrees. Okay, done with wet rag. So, I showed an animation last time. You're in a spaceship. And we did a light beam that went up. It bounced off a mirror and came back down. And this distance from here to here, if it takes a certain amount of time, and they often do this, if you go and study this stuff more, they call it a proper time. It's just so we can distinguish it, because we've learned time can be different in different frames of reference for the same event. Hence, they don't need to be simultaneous. The proper time is usually referred to the time measured in the frame of reference that's at rest, that you're at rest with respect to. You're not moving with respect to that reference frame. You measure the time, you get T naught, they call it, T sub 0. So that if it takes T0 time to go up and T0 to come down, what's the distance? How do we find distance? That change in position? It's the velocity times the time. We've been doing lots of that. That's from velocity is a change in position with time. So the distance here is the speed we're going. It's a light beam. That's its velocity. That. And over here, same thing. So it goes up CT and down CT. No surprises. In a spaceship that was moving with a certain velocity, what's it look like if you're in the ship? What will you see if you do the same experiment? If you're standing in the ship, what do you see? Up and down, but you're moving. Yeah, who thinks up and down? Who thinks diagonal? If you're in the frame, what happens in an airplane when you throw a ball up? What do you see in the airplane? It goes up and down. It's that idea. If you're moving with the same velocity, because you're in that reference frame, you still have v, you'll see it go up and down. Just as if you were here at rest. Because you're not moving here with respect to the frame, and you're not moving here with respect to the frame. So nothing's up, nothing's different for you in the spaceship. Now, the one you're thinking of is if you're still up here at rest, and you're watching this frame of reference go by. Now what do you see? That's the diagonal. Yeah, so it starts, but it had that initial velocity, so it had a component this way, and it starts going this way, so it's going to move at an angle. It'll go up, but the spaceship has moved over, and you get that distance. I'm going to redraw that. So you go up, you go down. We know what this distance is. It's CT naught. It's the same distance using T naught that time. The speed here is still c, but it takes a different amount of time. We saw that in the animation. Because it's covering more space, so it has to take a different amount of time to keep the speed of light as a constant. Yes, Glenn?
Those cases with the differentiation of time not around here,
Yeah. Do we ever notice these time distances? Yeah, it's a good point. Rarely do we ever notice this. We start to notice it when we get to what we call relativistic speeds, which hardly any of us ever deal with. What's relativistic? You probably wouldn't start seeing any of these effects until you were at least 10% the speed of light, which is really fast. Because the speed of light is really, really, really fast. And airplanes don't even come close to that. So yeah, we don't notice it much. We can detect it, though. They did an experiment where they took two really precise clocks. They were atomic clocks. And they left one here on Earth, and they took the other one up in an airplane and flew it around for a long time. And when it came back, they were running at different times. They weren't synchronized anymore. Why? Because one was going closer to the speed of light, thus in a different frame of reference. And time was different in that frame of reference. It had been dilated, stretched. That's what we call it, time dilation. And it was actually running more slowly from our frame of reference than ours. So when they finally came back together and they're in the same frame of reference, they were no longer simultaneous, in sync. Now, how much of a difference was this? Oh, I don't remember, but a really small fraction of a second, micro, nanoseconds. I don't remember, but it was detectable. So something I find neat with this is, all right, we can represent this distance with velocity and time, this one and this one. How about going along here? What's this side? What's our velocity in that direction? Yeah, a change in position over time. And the speed of the ship. We're in that frame of reference, so you're both correct. You have this velocity, and how long did we take to get to there? T. So you could think of this one as VT also, from there to there. Yeah, and that's the velocity was that this position is what we changed in that amount of time. In that direction, that was the velocity of the frame of reference, the moving frame of reference. Well, this is one way to get our factor difference of how things change with relativity. Here's a right triangle. So if you take VT squared, this side, plus CT naught squared, that equals the hypotenuse squared. It's Pythagorean theorem. There's nothing really complicated about how they get this factor. There's other ways they do it more rigorously, but this works and it agrees, so it's accurate. Now you play a bunch of fun algebra, which I won't torture you with. It comes out to be all that times the proper time. This factor here, 1 divided by the square root of 1 minus the velocity of your frame of reference, or more specifically, the relative difference in velocities between your two frames. Both frames could be moving, but this is the difference in the frame velocities between you two, squared, divided by the speed of light squared. We call that factor the Lorentz factor. And it's usually given this Greek symbol lambda. So we can write that so it doesn't look as scary like that. That's how much time dilates or is different from one frame of reference to another. So us watching our clock time tick by, we see this time. But in a spaceship or a jetliner traveling closer to the speed of light, it clicks at this time. What's the difference? It'll be this Lorentz factor. Can we figure out how much difference? Sure, if we knew how fast the relative motion was, we just plug it in and we got the factor. I made a little chart so you can get a feel for this. It's in your book too, because I'm not going to make you calculate them, but I'd like you to have a feel for this. Here's a few values. The Lorentz factor, the percent of the speed of light you're going. So if the Lorentz factor is 1, can you see that if this is 1, the denominator has to be 1. For the denominator to be 1, you have to be going, this has to be 0, right? So you just have 1 minus 0. So you have 1 over 1. That means you're not moving, or you're barely moving at all. So you're essentially going 0% the speed of light. That's what we're used to. The Lorentz factor is 1. Then the two times are identical for all practical purposes. And we never notice any of this relativistic stuff. If you start going faster, and you have a velocity now, the Lorentz factor will always be bigger than 1. Can you see that? If you plug in any value for v, it'll be, the Lorentz factor always comes out to be bigger than 1. Let's say it's twice. That is 87%, the speed of light. If it's 3, you're going 94.2. Here's a few of them. 4, 97, 98, 7.07 is 99. And how about one more? 10, 99.5. So if I plot the Lorentz factor with velocity as a percent of the speed of light, let's say that's the speed of light. As you get faster and faster and faster. Here's 1, here's 2, 3, 4, and we'll see if I draw this accurate. You start at 1, and it's pretty much 1. You don't notice any difference until you start going pretty darn fast, and then we don't notice, and then all of a sudden, which is why we don't really worry about the special theory of relativity in normal everyday life. This is where I like to emphasize. Does that mean everything we've learned is incorrect? Yeah. Max. This is the Lorentz factor. So that would be 1 or 2. It's the ratio between the different times. We call it the Lorentz factor. It really is this because tells you how fast you're going, or how fast you're going gives you this factor. In this class, I think it's fine to just deal with a number as a factor instead of having to calculate this all the time. Does that help? To equal 1? While I'm down, 1 would have to be over 1. So this has to be 1. For that to be 1, this has to be 0. So 1 minus 0. You have the square root of 1. Square root of 1 is 1. 1 over 1 is 1. So essentially, this is really, 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 really small compared to this. That would make this 0. Yeah. Which is, if it was 0, you're not moving at all, then yeah, the Lorentz factor is 1, and the times are the same. We don't even have to think about this. It's 1. You start going a little faster, it's still essentially 1. I'm not worrying about it until you start getting over to here. Now you have to include the effect because it's going to be noticeable. Did you know your phones would not work without the special theory of relativity? They have to start accounting for it. It's GPS, where it knows where you're at. The satellites out there, they're going faster. And the gravity's different, so the general theory of relativity comes into play also. And if they did not account for this stuff, they'd be wrong. They wouldn't be accurate enough. You know, the military used GPS and pinpoint where somebody's at. They'd be miles off if they did not correct by this factor. And anything that uses GPS, traveling in your car, hell, turn right in 500 feet. Recalculation. Would be useless without the special theory of relativity. Also, everything we've learned is still correct, but in a sense it's an approximation. Newton's laws and all that still hold, but in what case? We can trust Newton's laws when? Yeah, something with light. How fast we're going. If we're going normal everyday speeds, we don't see an effect. Why bother dealing with a special theory of relativity? We don't need to. We rely on Newton's laws. They're like an approximation at low speeds, but they're still true. But they break down by this factor that becomes more and more conspicuous the faster you go. So in this realm, when you're going near the speed of light, you can't use just Newton's laws. You'll be wrong. You'll be off. Then you have to account for the special theory of relativity. So special theory of relativity works at all speeds. Do you see that? But Newton's laws only work at slow speeds. So we don't have to deal with that. Make our lives easier. We just stick with Newton. But when you start dealing with big speeds, like the satellites, there's an effect now, and they account for it. Yeah? Yes, it does mean there's no way to actually reach the speed of light. It's an asymptote. This factor, you can plug it in. As v gets bigger and bigger and bigger and bigger, this gets higher and higher and higher and approaches. Let's pretend we were going the speed of light. This would be c, right? What's c squared over c squared? 1. What's 1 minus 1? 0. What's the square root of 0? 0. What's 1 divided by 0? Undefined. Or some call it infinity. That doesn't make sense. So the special theory of relativity predicts that you can never get to the speed of light. Or it breaks down at the speed of light. We have not been able to detect anything traveling faster than the speed of light that carries information or matter. I think other scientists might not like my next statement, but we don't know. This works up to the speed of light. It's a theory. And we use it for things we've seen, and it's been working beautifully. They test it over and over again. Maybe someday they figure out, discover something that can go faster than the speed of light. Well, they'll have to come up with a new theory to cover those realms. Because this only goes up to the speed of light. It says you can't go any faster than that. It's a good observation. Can you see that the faster and faster... Well, let me come back to that. So there's this paradox. Who's heard of the twin paradox? I was hoping more, because I was hoping you'd read it in your text by now. But so, it's two twins. It's fun. Remember I told you I saw those astronauts, Mark and Scott Kelly? Scott's been on the International Space Station for about almost a year. He'll come back next month. And his brother's been down here, and they're testing many things. But this is one where he's up there going a lot closer to the speed of light. We can exaggerate. Let's put you on a spaceship and you go cruising around at 98% the speed of light for a while, and then you come back home. You get off the ship and you look at me that stayed put, and I'll be an old person. And you'll just be a little younger. Because of this time dilation. Let's walk through this. I'm at rest, so time will tick away like we normally think. You hop on the spaceship, whoosh, cruising along. How will time seem to be different for you? Good. No, because in your reference frame, everything will still look normal. It's an inertial reference frame. The laws of physics apply. You'll watch, tick, tick. Things will seem normal to you because you're at rest with respect to that frame of reference. Here's the weird part. Me at rest, observing you. How do I see your time passing by? Slower. By what factor? If you were going 98% the speed of light compared to me, there's the Lorentz factor. I mean, that's 98% the speed of light, so the Lorentz factor is 5. So that tells me, boom, your time, I will see your time passing 5 times more slowly than my time. So 1001, 1002, 1003, 1004, 1005. There, a second just passed for you from my frame of reference. Does that make sense? So I see your time ticking away more slowly. The paradox comes in with, let's go to your frame of reference. What do you see? How do you see my time passing by? Oh, we got slower and faster. Okay. In my frame of reference, I'm at rest. So I don't confuse you. I'm in your frame now. In your frame of reference, we're at rest. So what am I doing back here compared to your frame of reference? I'm moving. Yeah, I'm moving relative to you. What speed am I moving at relative to you? 98% the speed of light. You can think of it as you're moving away from me at 98% the speed of light, or from your perspective, I'm moving away from you at 98% the speed of light. It's relative. So the difference is the same. So the Lorentz factor is still 5. You will see my time ticking away 5 times slower. It'll look like I am aging less to you. But to me, you look like you're aging less to me. Anybody yet? So my time's normal. I'm fine. Nothing seems odd. Your time to you seems fine because we're at rest with respect to our frames of reference. But we're moving with respect to each other. So I see your time as ticking away more slowly, and you see my time as ticking away more slowly. We both think the other person's staying younger while we age. But then they come back into the same frame of reference. You return from your trip, you get out of the door. Who's really older? Me, the one that stayed at rest. Why? There's a paradox. Why isn't it the other way around? Because on the trip, we're both right. But once we get back together, I'm the older one that stayed put. It's a subtle difference. I don't know if anybody... They were the ones traveling the speed of light. Well, from my frame of reference, yes, you were the ones moving. But from your frame of reference, as well as you know, your ship stayed put and the Earth receded at 98% the speed of light. So not only just that, but Glenn has an idea.
Well, since if you were to continue moving away at the same speed, it still wouldn't make it slower. It's about moving slower. But since you returned to their frame of reference instead of them coming to your frame of reference.
Yeah, it's because they come back to my frame of reference. From a third party, I see where you're getting. If there was a third party observing all this, they would see that the ship is the one that moved, not Earth. So I see where you're getting at. And yeah, it's because they came back and ended up back at Earth. The little catcher here is, do you remember in the video the difference between inertial and non-inertial reference frames? Funky things can happen in non-inertial reference frames where things accelerate. The ship has to decelerate, turn around, and reaccelerate. It actually went through 2 different reference frames. And that's where the difference comes in, is because they were the ones moving that actually accelerated. So they're the one that stayed younger. I'm the one that's older. But so that resolves the paradox. But that's an example of time dilation. Who read the Ender's Game? Anybody has read the Ender's Game? Oh, it's getting less and less each year. It's too bad. Do you remember the hero? I'll try not to have a spoiler alert too much, but they used the theory of relativity. They actually just mentioned it in the book. Those that read it, do you know what I'm talking about? Do you remember how long he was gone? Basically, he fought in a war. He learned something no one else did. And they know they needed his knowledge. They needed to keep his knowledge alive until they could train a commander that could go conquer these people. But they knew the new person, it was going to take a while to get somebody prepared. But they needed to know what he knew. They figured he would die before that happened. So you know what they did? They sent him into space at the speed of light. I think he said he was gone, in his frame of reference, he was gone 8 years. So he had to just sit in a spaceship for 8 years. He said he was bored spitless. Seemed like 500 years. Well, how many years passed for people on Earth at rest with respect to him? He said 50. So they had more time to raise up some generations. So what's the factor there? 50 to 8. Whatever that is. 6 something? Yeah. So let's see. Using the special theory of relativity, if the factor was different, they thought he was gone for 50 years had passed here on Earth, but only 8 years passed for him. So he was only 8 years older, but everybody else was 50 years older. They were surprised he could still be alive. that ratio is in between here. He had to have been going between 98 and 99% the speed of light for 8 years to have made that happen. Obviously, they were more technologically advanced, but but they used that in Ender's game. I thought that was fun. So something else happens. Lengths contract. We've just talked about time. Time dilates. Well, if time changes, we've already discussed how space is changing. And that ratio is it's called length contraction. If you measure at rest with respect to it, the proper length, we have a meter stick. Should have brought one in. We measure it to be a meter. If you take it on a spaceship and go 98% the speed of light, what do you measure the meter stick to be? A meter, because you're at rest with respect to it. Nothing's funky. But if I try to measure your meter stick on the spaceship, what do I get? I'm at rest, you guys are moving, and I try to measure the length of your meter stick. Will I get something longer, shorter, or the same? Shorter. Let's say you're going 98% speed of light. Factor's 5. You plug in 5 here, and I will measure a length a fifth the length of a meter. It will seem shorter. Likewise, if you try to measure my meter stick, what will you get? A fifth shorter. From your frame of reference, mine will be, I'm moving with respect to you. Now, it only goes in the direction you're moving. So if you are moving this way, then the contraction appears to be in that direction. It shrinks this way. It doesn't shrink this way, because you're not moving in that direction. There's no relative motion that way. So that doesn't work. If you were moving that way, it would contract by the component of the velocity in this direction and the component that way, and it would shrink both this way a little and this way. You take up less space. So you get time dilation and you get space contraction. What I like is thinking about somebody going the speed of light or near it. From our frame of reference at rest, time seems to slow down for them. They have all the time in the world to do whatever they want from our perspective. And they also have less distance to cover. So it's like they can go everywhere in a lot of time to get there. I like doing thought experiments. If you could go the speed of light, which is true as you approach it, but let's just say you could go the speed of light. What would happen to time from someone at rest's perspective? Your time. What would happen to your time going the speed of light from someone at rest's perspective? It keeps getting slower and slower and slower until you're going the speed of light. From our perspective at rest, it would seem like time stops for them. And it would seem like everything is in front of them because all space is contracted. There is no length if you were going the speed of light. So you'd have, you had nowhere to go because everything is before you, and you'd have all the time in the world to get there because time has stopped. It's kind of mind-boggling. Another change that happens, momentum is mass times velocity, inertia in motion. That holds true for non-relativistic speeds. What if you're going relativistic? It just changes by the Lorentz factor. So if you're going 98% the speed of light, that factor's 5, you're going to have 5 times as much momentum. Or look at it this way, it'll take 5 times as much to get you up to that speed, to change your momentum to get you to that speed, which is one way we can look at why it seems impossible to approach the speed of light. Because the faster and faster we go, the more and more momentum it takes. And it seems impossible to create that much energy. If you were to go the speed of light, you would need an infinite amount of change in momentum to get up to that speed, an infinite amount of energy. And we haven't figured out how to do that. I know we're out of time. There's one more equation. Probably the most famous equation in physics ever. Please raise your hand if you've never seen this. Exactly. The energy changes too. They don't throw the factor in. The factor here is this. Basically, and I'll discuss this more at the beginning of Friday, and then we'll move into review. But energy is the same thing as mass. Space and time now is like one's not preferred. Don't think of time well, you can think of time, but we like to think of time as passing by like water in a river. It's flowing. It just keeps on ticking. Well, you know how we move through space? To help me with this, I start thinking about, what if I was moving through time? I'm not just watching time flow by, tick by. I'm moving through it. Hence, my speed affects how time seems to me. So just like as you move through space, you're moving through time. It's similar between energy and matter. They're kind of like two sides of the same coin. You got matter, you got mass, there's energy there. If you have pure energy, it's like, I like to think of it, you could congeal it. Say it condenses, you need to have matter. They're one and the same. And the conversion factor, we've seen this before, is c squared. I wrote it right here. So you can think of it, c squared is that ratio. This isn't the speed of light, it's the speed of light squared. So this isn't a velocity. They're the same thing. They're totally interchangeable. This is another result from Einstein's theory of relativity. So I'll go dwell on this a little bit. Come with some good questions, and we'll review this and the rest of it Friday.